So last time, let's remember, last time we covered the mean value theorem, Rawls theorem, mean value theorem. I like to call it the easy pass theorem. What does it say in words? If you have a continuous function, if f is continuous on a closed interval and differentiable in its interior, then the average rate of change is realized instantaneously somewhere. Let's just write that down. The average rate of change is realized instantaneously somewhere. So the somewhere, i.e., in other words, there exists some point C in the interior such that the average rate of change over the whole interval, here's A to B, here's f of A, here's f of B, f of A, f of B. The average rate of change is f of B minus f of A over B minus A. That's this slope, is realized instantaneously. Instantaneous is f prime, somewhere being this this place C that we're hypothesizing. Okay, so there's some point C so that the instantaneous rate of change at C is exactly the average rate of change. All right, and you had a bunch of exercises with that. I hope you're feeling comfortable with that theorem. A special case of this is Rawls theorem. It is a special case, but that's not logically correct because we proved the mean value theorem from Rawls theorem. But a special case is if f of A is equal to f of B, then this numerator is 0. Okay, so if f of A is equal to f of B, if you start where you end, then at some point you must have had a derivative that's equal to 0. Same, but with f prime of C equal to 0. Okay, does that make sense? Let's use that to prove. So what we're up to now is curve sketching. The next topic is curve sketching, and the key ideas in curve sketching, there are really only two kinds of things that we will cover in curve sketching. I mean, maybe curve sketching is an ancient art form now that we have Desmos that we can just Google, but it's still useful to be able to, the tools that you will develop by learning to think about curves without necessarily needing to graph them will allow you to think about shapes that you're unable to graph. Okay, you might think like when there's no such thing as anything beyond 3 dimensions, and yet when you go to Netflix and they're recommending you the next Netflix series for you to be watching, what it's doing is taking 1,000 dimensions along which you might like, you like comedy, but you like dark comedy, but you don't want it to be scary, but you want it to have female lead or whatever it is, all the different things that they have learned from you. That's 1,000 dimensions of tastes, and they want to cater to you precisely. They're going to be doing something where 1,000-dimensional vector space, you can't visualize 1,000-dimensional vector space, but you can still understand properties of it. So that's the sense in which curve sketching is not something that's dead. When you understand the properties from things that we could check on Desmos, you'll be able to understand them on things that you can't. Does that make sense? Okay, so ideas in curve sketching, they're basically two ideas. One idea is, of course, are we increasing or decreasing? So slope being positive or negative. In other words, increasing or decreasing. And concavity. Are we increasing rapidly or slowly, or are we decreasing rapidly or slowly? So concavity, which is about the second derivative being positive or negative. We're going to say all of these things in much more detail. First, let's just prove a theorem, which again, I think people find obvious. Some people call this the first derivative test for extrema. I'll explain in a second what I mean by that. So here's a theorem. if f is continuous on a closed interval a to b, and f prime exists and it's differentiable, exists on the open interval a to b, and f prime is always positive on that interval. So if you have an interval on which the derivative is positive, then f is increasing on the interval a to b, on a to b. Okay, and the proof is very simple. Again, it's like, why do we need a proof for this? Well, we've been using hopefully our intuition has developed to the point that it's clear. But actually, how do you rigorously prove something like this? Rigorously in quotes. If you think about 2 points, so I have a point A and I have a point B. If I look at any pair of numbers, x1 and x2, x1 and x2 in the interval, so fix any x1 less than x2 between A and B. What I want to know is that the value of f at x2 is greater than the value of f at x1. That's what increasing means, right? Let me restrict my attention to the subinterval x1 to x2. Now, by the mean value theorem, there exists some point C in the interval x1 to x2. There exists some point C in here, such that what? F of x2 minus f of x1 over x2 minus x1, this is the average slope from x1 to x2, whatever's going on there, is equal instantaneously to this derivative point C. Does that make sense? That's the mean value theorem applied to the subinterval x1 to x2, where the function is differentiable and where it's the continuous on the closed interval, differentiable on the open interval. Okay, but that means that f of x2 minus f of x1 is equal to f prime of C times x2 minus x1. Why are we done? We're trying to show that the function must be increasing. We showed that the value of x2 minus the value of x1 is equal to this thing. Okay. Yes, we've assumed that the derivative is always positive. So this is positive. This is positive because we assumed x2 is greater than x1. So this is positive, which means that f of x2 is greater than f of x1. This difference is positive. So we have to have increased from x1 to x2. That's true for any point x1 to x2, which means the function is increasing. Okay. Any future value is greater than the previous one. All right. So that's the kind of theorems you can prove using things like the mean value theorem. But really what it tells us is this is what's called the first derivative test. First derivative test is that if f prime, let's say a function is differentiable, if f prime changes from being positive to being negative, let's say at a point C, at C, then what has happened at C? The derivative was positive. We were always increasing until we got to C. Then we got to C, and the derivative is now negative. We're always decreasing. Of course, there's the same theorem with greater than replaced by less than 0 and increasing replaced by decreasing. So we're always decreasing. So C must have been a maximum. What kind of max? Absolute? No, I don't know anything about absolute. All I know is about in the neighborhood. Then C is a local max. Okay, and if f prime changes from minus to plus, then C is a local min. Okay, great. Then we have a second derivative test. So a second derivative test, if instead of looking at how the function changes, you look at, so if f prime of C is equal to 0, let's say the derivative at a point is equal to 0, I want to look at whether that point C is a local max or a local min. So here's a point C. The derivative is 0. So how can I tell if it's a local max or a local min? By looking at the second derivative. This is the second derivative test. Then there are three things that could happen. The second derivative could be positive or negative, or it could be 0. So in these three cases, what are the three things that we can conclude? So if the second derivative test is positive, if the second derivative of a critical value is positive, anybody know? If the second derivative is positive, that means that the first derivative must be increasing. If the first derivative is increasing, but its value is 0, it must increase from a negative to a positive. So we must be a local min. We must be a local min. Okay, so we must be decreasing until we get to C and then increasing after C, because the first derivative has to be increasing. Applying the first derivative theorem to the first derivative, which means we look at the second sign of the second derivative. Okay, so this is a local min. The way I like to think about it is just think about the function x squared. X squared is a function that's going to have second derivative being positive. Second derivative is 2, where the first derivative is 0, namely at the origin. Okay, and that's a local min. So it's a happy parabola. What about if it's negative? If the second derivative is negative, that means the first derivative is decreasing. You decrease from positive to negative values if you're gonna be passing through 0. So then this must be a local max. Local max. Okay, so this is the graph of negative x squared, which is sad parabola. And what about if the second derivative is 0? Then what can we say? What's that? Could be either or neither. Could be so inconclusive. And the three examples to keep in mind. So examples to keep in mind are x cubed. So what's the graph of y equals x cubed at 0? So the first derivative, y prime, is equal to 3x squared. Y double prime is equal to 6x. And if I evaluate this at x equals 0, both of them are 0. And is 0 a max or a min? Neither. It's neither a max or a min. There are values nearby that are lower than the value here. There are values nearby that are higher than the values here. Okay, it is an inflection point. We're going to talk about those in a second. So that's one example for why this can be inconclusive. Another example is y is equal to x to the fourth. X to the fourth looks like x squared squared. So it's an even flatter parabola. And y, the first derivative is 4x cubed. The second derivative is 12x squared. And both of these at 0 are 0. And this is a local min, in fact, a global min, as opposed to y equals negative x to the fourth. That's the same thing, but just the other way. Okay, so really inconclusive. It may be a local max. You just can't tell. It may be a local min. You just can't tell. It may be neither. Okay, so the second derivative test tells you nothing if the second derivative doesn't have a sign. With these sort of caveats, you can think about basically you can graph like all kinds of things without a calculator. So let's try a couple of graphs. You guys want to let's do one. You can get in trouble when you try to graph things. Let me graph things that you graph just out of thin air. You'll see in a second why. Let's graph x cubed minus 12x plus u minus 5, whatever. Okay, let's graph this as best we can with all the information available to us. All right. Compute the derivative. Take 5 seconds and compute the derivative. Give me a thumbs up when you're done. Okay, that was easy. 3x squared minus 12. So let's factor this. Let me pull out a 3. I have an x squared minus 4 left over. And of course, that factors as 3 times x minus 2 times x plus 2. This is what I mean by if I hadn't cooked it up like this, then we'd be solving a quadratic and wasting some time doing so. Fine. What about the second derivative? The second derivative, it's not so nice to compute from here, but it's very easy to compute from here. Take 30 seconds, 10 seconds, 5 seconds, 1 second. Just write down the second derivative. Give me a thumbs up when you got it. Okay, great. 6x. What are the places where I'm worried about? So my critical values. Remember what critical values are? Where f prime is equal to 0 or it doesn't converge. Yeah, undefined. Or doesn't exist. Maybe is a better way to put it. Does not exist. Okay, so what are they in our case? 2 and -2. Yep, -2 and 2. Okay, those are our critical values. Now, when is the second derivative equal to 0? 0. So that's also going to be an interesting point for us. That is a point where we change from being concave up to being concave down. You see, being a local, if the second derivative is positive, yeah, I skipped over the fact that this thing about inflection points. We'll see it in practice. We'll see what's going on in practice. So something to look at. This is a new topic that we're going to, a new bit of terminology. Inflection point. Inflection, not a critical value, but an inflection point or potential inflection point is at x equals 0. So I would just graph. I would put those 3 values down first. So what is going on when at x equals -2? -2 cubed, -8, minus 2 times 24, 2 times 12 is 24. Negative times negative is positive. So I have a positive 24 minus 8. 16, 16 minus 5, 11. So this is at -2, 11. Okay, how about at 0? -5, -5. And how about at 2? 2 cubed is 8. 2 times 2, 12 times 2 is 24. -24, 8 minus 24 is -16. Minus 5, minus 21. Okay, that's all the way down here somewhere. -21, 2. Okay, so this is 2, -21. I have 3 points, and from those 3 points, I will be able to figure everything out about this graph. All right, let's look at y prime. And what I like to do is just draw a little number line, and think about what's going on. If I'm less than -2, do I have a positive value here or negative? So if you look at the components, this is always positive. X minus 2, if I'm less than -2, what's happening to this? Less than -2, subtracting 2, I get a negative value. X plus 2, when x is less than -2. So negative times negative, positive, positive. So I'm increasing when I'm getting close to -2. How about when I'm between -2 and 2? This one is, if I'm bigger than -2 and then I subtract 2, if I'm bigger than -2 but less than 2, if I'm less than 2 and I subtract 2, negative. And what about x plus 2 when I'm bigger than -2? Positive. So I have negative and positive. When you multiply those together, negative. And how about bigger than 2? Now it's just positive, positive. Okay. So now it's clear what's going on. At -2, we have it went from positive derivative to negative derivative, local max. Okay. Or if we look at the second derivative at -2 is, so y double prime. Let's look at y double prime at -2. So let's look at y double prime. 6x, that's a double prime. 6x when x is -2. -12, that's negative. At 0, I have 0. And what about at positive 2? 12, which is positive. Okay, so the second derivative test, if I look at the second derivative test, I know that the derivative is 0 at -2, And the second derivative is negative, which means second derivative is negative. So we have a local max, we're concave down. Okay, that's exactly what I've drawn. How about here at 2? Positive, concave up. All right, and now we can really graph the whole thing. So we have a local max at 211. We have a local min at 2, -21. At 0, I have an inflection point. An inflection point that changes from a concave up. So this is concave up, meaning it looks like a parabola like this. And here we're concave down. Concave down, which means we look like that. So I'm sort of concave up. Of course, this 5 and 21 are not to scale. So I'm struggling to get it to be concave up. And then it's x cubed. X cubed is what's going to dominate. So eventually we're just getting larger and larger, and we're doing so faster and faster. So this is like a cup until it gets to 5, and then it switches to being concave down. And then we're concave down. Okay, so we're concave down. Right here, we switch to being concave up. And then we grow like that. And that is basically the picture of this. Does that make sense? We're going to do a whole bunch of pictures. Should we check this picture against Desmos? What is it? X cubed minus 12x minus 5. X cubed minus 12 x minus 5. And here is the picture with all the features that we saw. At -2, we have our largest point at 11. At +2, we have our lowest point at -21. And at 5, we switch from being concave down to being concave up. You see that? Cool. Should we do a couple more? All right. So inflection point is where you switch from being concave up to concave down. A couple more examples. Here's a good one. All right, let's test our metal a little bit. Y is equal to, or f of x is equal to x plus 1 squared over 1 plus x squared. Okay, so this is not a polynomial. Why don't you take a minute? Oh, let's make this the quiz. Compute the derivative and the second derivative. Come on, this is an easy quiz. This is just like, do you remember the quotient rule? You can do it by logarithmic differentiation if you so choose. There's all kinds of ways to do it. This should by now be easy. Try to simplify as much as you can, because we're going to need the information out of it. We'll need to know when it's positive, negative, and it's hard to compare plus signs when there's positive, negative. It's much easier to look at factors. This factor is positive, that factor is negative, so their product is negative, that kind of thing. Give me a hand if you need help. I think at this point, nobody needs help with this. Give me a thumbs up when you're done. Hold on. I suggest you simplify y prime as much as possible before you continue to differentiate a second time. How many are done with y prime? The first derivative. Let's make sure we all got that one right before we continue to the second one. So did you do it by logarithmic differentiation or just directly? Either way works. What'd you do? Quotient rule. Let's do quotient rule. I think that's easier in this. Okay, so bottom times the derivative of the top. Derivative of the top is 2 times x plus 1, and there's no chain rule, minus the top x plus 1 squared times the derivative of the bottom, all over bottom squared. Oh God, what do we have here? I have an x plus 1 in both factors. So I'm going to pull that x plus 1 out. X plus 1. I'm not going to have room. Okay. Let me pull that x plus 1 out of both places. I have the denominator, 1 plus x squared squared. What's left when I pull this x plus 1 out? There's a 2x squared plus 2 minus one of the x plus 1s is gone. So I have a 2x squared. It's actually not so bad. Minus 2x. So these are gone. So I think the 2 pulls out. And I have a 1 plus x times 1 minus x. I think so I think for differentiation purposes, for the purposes of differentiating it again, it's better to combine those two into that. Did anybody get that? For the first derivative? Okay. Give yourself a point and continue. Once you have this, now continue to the second derivative. If you don't simplify the first derivative in a reasonable way, it makes it much, much harder to compute the second derivative. Done. Anybody there? Right. I think some people have it already. Should we do it together? Quotient rule or logarithmic differentiation? I think quotient rule on this one too. Okay, bottom 1 plus x squared squared times the derivative of the top. Well, there's a factor of 2. Let's just put that 2 all the way outside. No need to carry that around. Derivative of the top is minus 2x, just minus 2x, minus top times the derivative of the bottom. Oh boy, 2 times 1 plus x squared to the 1 times the derivative of what's inside, 2x, all over 1 plus x squared to the 4th squared. Yeah, you said. This. So I took this initial 2 and I pulled it all the way out. So I'm just zooming in on this bit. So you're absolutely right. I just pulled it out. Okay. What do I see now? I see this 2, I see this 2, and I see one of these 2s. Let's take this one or something. So that's a factor of 4. So underline means I've taken care of it already. I see a 1 plus x squared, and a 1 plus x squared, and a 1 plus x squared to the 4. So let me pull out a let's do it in one step at a time. So this is a 1 plus x squared to the 4, but let me pull out a 1 plus x squared from the numerator. So this I've taken into account, and this I've taken into account. What's left is negative x times 1 plus x squared. So that's negative x times 1 plus negative x times 1 plus x squared times x squared. So now I've taken this whole thing into account. Minus, there's a factor of 2. There's a 1 minus x squared times x. So is that an x minus x cubed? Hopefully someone is checking that I'm doing this right. Is this what you got? Something like it? Sure? Did you get something different? Well, it's hard to tell until the dust settles if you did it a slightly different way. Who knows? Who knows at this point? Who even knows at this point? All right. It's too ugly. It's not that ugly. It's not that good looking either. We must admit. There's an, okay, wait, how many, what's going on here? I have a plus 2x cubed and a minus x cubed. I also have a minus 2x and a plus x. That means I can pull out an x. So I can pull out an x from everything. Now I have a minus x cubed and a plus 2x cubed. So that's a plus 1x cubed, but I pull out an x, so that's an x squared. And then here is a minus x and a minus 2x. So that's a minus 3x, but I pulled out an x, so minus 3. Is that really what it? Anybody get this? Okay, good. No? Something like it? But okay. Did you not get it only because I simplify algebra? I think that's one thing that I definitely do too fast for some of you. That's okay. If you would have taken 3 more lines to get to the same answer, that's fine with me. As long as you would have gotten the same answer, I hope. Everything that cancels, and you can factor out an x. You did it with log derivatives? I think this one's actually harder to do with log derivatives. But yeah, all right. Anyway, we do know how to compute derivatives, right? Can we pass those down to the end? Give yourself a point for the first derivative, give yourself a point for the second derivative, if you followed along. And Shay, right? Yeah, so Shay's gonna put them up here for me. Okay, that whole exercise was so that we could do the graph sketching. So again, let me copy the function itself. Here's the function. Hello. Paste? No? No? Let's try again. Copy. Paste. Thank you. There's the function. Here's the first derivative. Where's the first derivative? Over here. Uh-oh. Over here. That's the first derivative. Okay. Was that minus sign there? It was. No, that was part of an equal sign. Oh, I could do a lasso instead of a box. You guys are too smart for me. I don't know how. If I click it again, I'll get the right thing. It's okay. If I click on the lasso tool, all right, you guys are gonna have to teach me after. Right now, I'm not gonna learn it fast enough to implement it. Nah. Do I have room for everybody? Slide over. Anyway, it doesn't matter. We know what the derivatives are. I just want to be able to see them all. Okay, that's the first derivative. I'm sorry. That's the function itself. This is the first derivative. This is the second derivative. Okay, let's go to town. Where are the critical points? Critical values. When can this be 0? Do I care about the denominator? No. Quotient is only 0 if the numerator is 0. Where is the numerator 0? 1 and -1. So C equals plus or minus 1. So I'll have a graph for y prime. The only things that I care about is the sign. So what's going on here? If I'm within -1, 1, then x squared is less than 1. So 1 minus that is positive. And if I'm either less than -1 or bigger than 1, then this squared is going to be bigger than 1. The numerator is always positive, right? X squared plus 1 squared is always positive. So the denominator is all I'm worried about, and this will be negative. So this is negative whether I'm bigger than 1 or less than 1. Great. If I was decreasing and then I become increasing, then I was a local min. If I'm increasing and then I become decreasing, local max. Okay, so at 1 and -1, I see local mins and maxes. Let's check that against y double prime. So where are my potential inflation? Words, help. Inflection, thank you. Inflection point, inflation point. Where's my inflection point? When can potential inflection points? 0. So I'll just say x. X is equal to 0 or √3, plus or minus √3. Okay, so y double prime. Now √3 is 0's here. √3 is bigger than 1. So it's a little bit to the side of 1. I try to line these up. It makes things a little easier to see. Okay. Without doing anything, I can tell you what the sign of y double prime is, because I know at -1, it should be concave up, which means the second derivative should be. Think about what function has looks like this, x squared. So two derivatives of x squared are 2, which is positive, right? But let's just check. If I put in -1 for x, then this is negative. This is also negative. The denominator is always positive. Okay, so I'm positive here. How about here? Concave down. That's -x squared. So I'm expecting this to be negative. If I'm positive, but less than 3, this is still negative, and this is positive. So now it's negative. What's happening above square root of 3? Positive and positive. So this is positive. So I do have an inflection point here. I change from being concave down to concave up. And how about here at negative square root of 3? This is positive, but this is negative. So I'm like that. Okay, so I have a couple of inflection points, and we're ready to graph. I'm worried about the point 1. What's happening at the point 1? What's happening at the point 0? 1, 0, 1, 0, 1. There's a point, 0, 1. That's going to be an inflection point. What's happening at 1? I have 2 squared is 4 over 2. 4 over 2 is 2. So this is the point 1, 2. What's happening at -1? -1, that's easy. That's 0. So -1, 0. Square root of 3, I don't need the exact value of square root of 3. 1 plus square root of 3 squared over, I don't know. What's going to happen after 1? It's going to, after 1, it's going to decrease. Okay, it's going to decrease. So at this 1, 2, I have a local max. At the -1, 0, I have a local min. What's going on as x goes out to infinity? Asymptotes. Horizontal or vertical asymptotes. So what are my horizontal asymptotes? Yes, what happens? What's the largest exponent? I have x squared on top, I have x squared on bottom. So the ratio of those is 1. Yeah, so y equals 1 is a horizontal asymptote in both directions. What about vertical asymptote? When is the denominator equal to 0? Never. It's always positive. So none. None. Okay. Now look at what's going to happen. I have to be asymptotic over here. Here I'm concave down. At some point I have to switch from being concave down to concave up. Where would that happen? √3. That's exactly this change right here. So this was 1. This is √3, which is between 1 and 2, right? 2 squared is 4. So somewhere over here, whatever that point is, I don't need to know where exactly that point is. We switch from being concave up to being concave down. I'm sorry, from concave down to being concave up. Concave up means it's a bowl. Concave down means I think of like where it's headed. It's headed down on either side. Okay. What's happening at 0? We have to switch from being concave down to being concave up until we get to this local min. And now what's happening at negative √3? We switch from being up. We're increasing. I mean, we're increasing to the left, meaning decreasing. And then at √3, we switch from concave up to concave down. And that should be a pretty close approximation to this curve, x plus 1 squared over 1 plus x squared. Let's just see it, and then we're out of here. X plus 1 squared over 1 plus x squared. And there's the graph. Not bad. All right, guys, get some good practice with this.